saying you're viewing Ethan Lake's screen. You see right above the title, the view options.
Yeah.
So not quite, but maybe.
I think it's fine.
It's fine. It's fine. We can see it. Don't worry.
Okay.
Ooh, there. It's a little bit
better.
Yeah. I think so. Did you see that?
Yes. Yes, it's on YouTube. Yeah, okay. Okay, more people today. Great.
Yeah.
So it's our great pleasure to have Ethan Lake from MIT. Ethan was a final year PhD student from Temple School, and he had broad interests range from condensed matter or quantum many-body physics, quantum information computer science, and quantum field theory. Today, he will talk about RG quantum circuits.
Yeah, thanks, Idra, for inviting me. Yeah, she said, like she said, I'm at MIT, but despite biking through campus like N times, I've never actually been here, so it's cool. Thanks for giving me the chance. And yeah, today I'm going to talk about some stuff which is a little bit kind of outside of my traditional comfort zone, which is more like quantum matter, field theory, stuff like this. So I'm not like huge expert on this kind of in the kind of field that I'll be talking about, but anyway, so the point is that it would be fun to discuss with people if they have any ideas, suggestions, comments. Yeah, so I'll just click it. So let me first just tell you guys who this work was done with. It's been with two people that I've been hanging out with a lot over the last year. Soonwon Choi is faculty at the QI group at MIT, and Shankar is a grad student in the QI group. And we've been doing all this fun, crazy stuff. They've taught me a lot about like information theory and all these things. So today I'm just tell you guys about one of the things we've been working on. And okay, so I'm just going to start with a few slides of like philosophical motivation, right, to kind of tell you what kind of the broad brush stroke of the talk is going to be about. It's going to be about a problem that is very common in physics, especially the type of physics that I do, which is like thinking about the relationship between sort of short distance, maybe microscopic physics, and long distance, more universal low energy physics, right? Usually the way we would say this is about the relation between the ultraviolet and the infrared, right? And there are kind of like 2 points of view that you can take when you think about this relationship, right? One kind of point of view is you can imagine like describing how one goes from the UV to the IR, right? So like, you know, you're handed the Hamiltonian of some like super complicated system of strongly interacting electrons, right? And your job is to turn that into some kind of like human interpretable form, which says like the physics of the systems at large distances is X, where X is some simple thing, right? This is kind of like usually what I do as a condensed matter person, right? We have some system, microscopic system we're interested in. We want to figure out the universal properties it has, right? But you can also kind of like conceptually think of going the other way also, where your starting point is not a microscopic Hamiltonian, but your starting point is like some simple physical model, like maybe the equations of hydrodynamics or like the field theory of a Dirac fermion or something like this, right? And then what you do is you try to find out how you can like hide it into some microscopic system, right? So you could imagine that I've like hidden the equations of hydrodynamics in the Hamiltonian for water molecules or something, right? It's kind of a weird way of presenting it because usually we just think of them in terms of some like IR stuff, but you could also imagine it from this perspective. Okay.
I have a question.
Yeah.
From going from IR UV to IR,
yeah.
Is it like given a UV theory, the IR is kind of known what kind of emergent behavior is going to appear?
Yeah.
But
you want to
from IR to UV, by hiding, we can hide it in more than one way, right?
Yeah, exactly. So like one of these, the UV to IR is kind of like not in an invertible mapping.
Yeah. So
right? So how can you go back and forth between them when it's not invertible? Yeah. So that'll come up in the yeah. Kind of basically what you were saying is that when we think about going back and forth, we really just mean going from the UV to the IR, right? And we do this with some kind of like renormalization group flow. That's like the name that we give to this like UV to IR mapping, right? That what kind of exactly how that flow works could look different in different contexts, right? It usually depends on like what kind of degrees of freedom you're sort of coarse graining over, right? And in the usual way that which we discuss it, it's not an invertible thing. You're kind of losing information when you do it. Anyway, but we're going to be thinking about this kind of problem of going back and forth between the UV and the IR today in this talk. And the kind of context in which this is going to be occurring is in kind of a context that, again, as I was saying, I'm not really like it's not something that I historically have done all the time, but it's within the context of sort of quantum circuits. And we're going to really be thinking about this UV to IR mapping as occurring at the level of wave functions directly rather than like Hamiltonians and effective theories and stuff like that. Right? So I kind of like when I was like my education in physics was like centered in like quantum field theory. That's when I was like becoming a physicist, that's what I was really interested in. And when you're doing QFT, it's like this renormalization group flow is always something that you do when you like integrate out high energy degrees of freedom and then coupling constants and Lagrangians flow and stuff like this, right? And that's there you're talking about like the flow and effective Hamiltonian or a Lagrangian. And that's not what we're going to be doing. We're going to be thinking about performing this kind of flow directly on like a quantum state. Okay. Yeah.
So should I think about this as some sort of block spin renormalization?
Block spin we're going to be kind of, it's more, yeah, basically we're going to be trying to think about how do you do block spin renormalization on wave functions, essentially, yeah. Yeah, indeed, the emphasis being on this, the kind of this state or the distribution of spins themselves rather than like the Hamiltonian which produces the spin. And yeah, so this is kind of just, this is a little bit of kind of like propaganda. It's not necessarily exactly what we're going to be doing, but if you like the thinking about error correction and these kinds of notions, you can kind of think of, have this notion of error correction in the back of your mind during this talk. So what we're going to be kind of doing is viewing like, you know, that different IR physics can be embedded in the UV in different ways, and the different ways in which you can embed that in the UV differ by some kind of like errors. And when we talk about going between the UV and the IR, we're going to be thinking about either like, you know, kind of decoding or encoding those errors. Anyway, so there's some kind of like error corrective perspective that if you like, you can just be thinking about in the following. So here's an outline for what we're going to do today. So I'm going to start by kind of recasting this sort of vague philosophical motivation within a slightly more specific setting, which is the setting of this quantum phase recognition problem that we're going to be trying to solve. And then I'll talk about kind of using these quote RG circuits, which we're developing for some very simple example with this Ising model. And then depending on time, I'll talk about applications of these ideas to kind of some more sophisticated examples. Okay, so let's start with this quantum phase recognition part. Okay, so here's the setting of the problem. So basically, the setting of the problem is that we imagine that we find ourselves in the possession of some black box, which outputs ground state wave functions for some unknown Hamiltonian, right? And what we want to do is we want to tell what phase of matter these wave functions are ground states of, right? So we have our box. You imagine like we have this box, and inside the box we have like one of Misha Lukin's grad students with their like next generation atom array thing, right? And they can produce wave functions, but they have like no idea what it is that they're simulating, right? And so our job is to tell them what kind of phase of matter their simulator is realizing, but we only get access to the wave functions that come out. Okay. So we want to understand how we can make some smart comments about what the wave functions look like, right? So this is not that hard of a problem, right? We just want to know like, is the thing in the black box that's producing these wave functions, is it the Hamiltonian for like a insulator or a superconductor, or some very general question like this, right? It's a very, very simple question. So that's the problem. And we want to develop some algorithm which solves this problem, right? Which tells us what phase of matter this wave function belongs to. But we want to develop a good phase recognition algorithm, right? So for us, what do we want? What kind of like desired properties should we demand? Well, one is we want this algorithm to be efficient in some sense, right? So meaning that we want to have to query this black box like the minimal number of times possible, right? So every time we query the black box, we have to like pay the grad student $10,000 or something. So we need to minimize the number of wave functions that we use, right? You can imagine that one strategy is just like get a bajillion copies of the wave function, then I just know exactly what the wave function is, and then I'm done, right? You can do more powerful things if you have tons of copies of the wave function. We're not going to do that.
Can I ask a question on your previous slide about how
Yeah.
it works with superposition and mixture? So like,
yeah.
if I have a state that's
Yeah.
a superposition between a paramagnetic state with
And,
respect to some Hamiltonian
yeah.
and a
Something else.
superconductor.
Yeah.
How would this thing?
So we're given the promise that we're given ground states of local Hamiltonians.
And the statement is that ground states of local Hamiltonians will always be precisely in one of these phases.
Yeah. Or if you want even more, maybe I'll have to say that we have a certain list of the different kinds of phases that it can be, and we're promised that the ground state is within those set of possibilities. But I think we could also just say that we know it's the ground state of where we want to go. Is we want to say your assumption is that it's the ground state of a local Hamiltonian, then tell us what, make some smart comment about what the phase is. But for the purpose of this talk, maybe I'm going to also add some extra constraints, like here's a phase diagram and the wave function is from somewhere in the phase diagram.
That's great. Thanks.
We can allow the wave function to be. Yeah, I didn't want to get into details about this, but we can also allow it to be a mixed state. It doesn't have to be a pure state, but that is getting into some details. Yeah, so we want to use as few queries to the black box as possible, right? But we'd also like this approach to be kind of like universal, this algorithm to be universal in some sense, by which I mean like, we don't want to just like machine learn our way through the problem, right? Because then we might not, we don't want to replace our like algorithm that does phase recognition with another black box, right? We want to, I mean, this problem we're trying to solve is not that hard, right? It's just binary yes or no insulator or superconductor, like something very, very physically very trivial like that. So we shouldn't have to rely on these very general, very high powered things like tomography or some machine learning approaches like that, right? So it's kind of a simple physics problem. So we should use some like simple physics based algorithm. Okay, so that's kind of like the overall goal, right? But of course, what we actually do in the paper that I'm talking about is much more modest. So what we actually do is we construct some algorithm which checks these two boxes, but it works for basically one-dimensional phases of matter with energy gaps, right? So most phases of matter are not one-dimensional and gapped. Okay, but we just are kind of like are holding ourselves to the standard where we want to try to like prove that things that our algorithms work, right? So we're starting off with some kind of like baby example of one-dimensional system. So you could think of like the, like a simple example would be like the Ising model in one dimension or something like this. But there are these other sophisticated examples with these symmetry protected topological phases that kind of make things less trivial, but yeah, that's going to be the last part of the talk. Anyway, so this is what we're going to try to do. And let me just now illustrate this. Maybe it's kind of already obvious, but let me just hammer this home by just giving you a picture of like what we're trying to do. So we imagine that, going back to your question, let's just specify to the case of I know that my wave function is going to come from some kind of like parameter space, some phase diagram that looks like this, right? This parameter space is basically like the space of all Hamiltonians that could possibly be occurring in our black box, which could be some like infinite dimensional space. I'm just going to draw some two-dimensional space here, but we're going to get wave functions from here. And suppose like a priori, we know that it's this parameter space is broken up into a few different phases of matter. So phase 1, 2, 3, on and on. There could be many. And let's try to just design an algorithm which tells us whether or not the wave function that we get is from this phase 2, right? Okay.
Sorry, so the input that you're given
Yeah.
is a state.
Yeah.
And so it's not a Hamiltonian.
No, not Hamiltonian. If you like, you could like, just to kind of like discuss like the spirit of what our algorithm should do, right? If you liked, I give you many copies of the state, you could just like learn what the Hamiltonian is, and then start from that Hamiltonian. Then you know what the Hamiltonian is, and then you could like figure out everything about there is to know about the spectrum of the Hamiltonian stuff. But that would be way too hardcore.
I was going to suggest the opposite. If someone gives you the Hamiltonian, and you have a promise that you have a gap in your Hamiltonian in 1 + 1,
It's easy to
then
find.
you could use this like Mazarani-Wittig-Landau or HESP algorithm to find the ground state in polynomial time with a classical computer.
Yeah.
And then once you have the ground state, then implement the rest of your algorithm.
Yes, but
You don't have to.
That's fine. You could. So whether or not you're given the Hamiltonian or not given the Hamiltonian is kind of like not that big of it. I think I prefer to imagine we're not giving the Hamiltonian. We don't know what the simulator is. It's just producing these wave functions. We just start from there.
I guess the time when it is a big deal is when your system is gapless,
Yeah. So which I'm conveniently
which you're not.
avoiding. We have some ideas about some simple kinds of gapless systems you can think about. Fermi liquids, for example, or other kinds of systems where you could try to like do this kind of same approach, right? For technical reasons, I'm just specifying to this gap space thing for now. But, yeah. So suppose we want to just identify whether or not the wave function we get is from this space 2. Okay. So what we have to do, well, the strategy that we're going to take, right? We're not going to try to do machine learning or tomography or whatever. Strategy we're going to take is to try to design some kind of like RG flow, which operates at the level of wave functions, right? That's what I was talking about, RG flow to begin the talk, right? So basically, we're going to try to design some kind of like flow on the space of wave functions, whereby if I input a wave function, say at some random point on this space that I'm interested, it'll kind of like, this machine that we design will kind of flow the wave function to the fixed point that we're looking for. So each phase will have some fixed point, and we want to design this map which performs this flow. So I haven't told you how that works yet, but that's what we're trying to do. So in particular, if we have, if I give you some wave function psi in this phase that I'm looking for, and some other wave function psi prime, we want them to both kind of like flow to this same fixed point, right? And the idea is that these fixed points will be like, when you get to this fixed point, it'll be like really obvious what phase you're in, right? So maybe I give you the wave function for some insulator, but somehow it's like really not obvious that this actually has like vanishing conductivity because it's not like a super simple wave function. But then I design some flow which flows it to like a really obvious product state wave function where it's very clear that it's insulator, right? So that's kind of what we want to do. Set up a flow which does that. Okay. Okay, but I said we want to do this with a quantum circuit. Like we kind of imagine we're given this wave function, then we have like we can just perform arbitrary quantum gates on this wave function, right? So we're doing this with a quantum circuit. So this diagram on the board doesn't really make sense because quantum circuits are unitary operations. So this looks like a very irreversible thing to do, right? Just as you were saying, RG flow is not a reversible thing. So why am I drawing this, right? So the solution that we, the way out is kind of as follows. So we designed this circuit. I'm going to write it as Q. What it does is it basically accounts for this reversibility in the following way. What it does is that when you input a state psi, it'll basically take psi and it'll output the fixed point wave function on some sub region of the wave function, and the rest of the system will be used to like store all the data which distinguishes like psi from psi prime. Right? So psi and psi prime could definitely be orthogonal. I can't flow them to the same state with a unitary transformation, but they both belong and if they're both in the same phase, I can take that part of them, which distinguishes them as being in the same phase, and put that on like one chunk of the system, and then put all the garbage, the non-universal garbage, on the other chunk of the system. Does that make sense?
The one question, this Q is same for all the three phases or just for one particular phase?
Yeah, it's going to be easier if we just say make a different queue for different phases. So how this is going to work is like, we are going to demand that if you give me something in the yellow region, then it flows to that fixed point. And if you give me something that's not in that region, then it flows to something else. So it flows to somewhere else, but we're not going to care necessarily whether it goes to some other distinguished fixed point. So this is kind of like a entanglement refrigerator. I think this is kind of like one way of kind of summarizing this, right? What we're trying to do is we have some, you imagine that the wave function I give you is like the fixed point wave function, but you've applied like a bunch of errors to it and you've made it more complicated, right? And what we're trying to do is we're trying to like suck out those errors and like refrigerate them away by pushing them off to one part of the system. So we're kind of trying to suck out all of the non-universal entanglement and put all the non-universal stuff, kind of isolate it away and keep the universal stuff in some subsystem. Okay. That idea good for everyone? So yeah, that's I'm gonna skip that.
There's a question in the chat.
Oh, are these ancilla degrees of, so, oh yeah, thanks, Arco. Yeah, he asks if the ancilla degrees of freedom are in a product state back here. The answer is that no, they don't necessarily have to be in a product state, right? So they will, basically the stuff that's in this kind of waste subspace could have a lot of correlations within itself, right? It'll be, if you start with some state that has a lot of non-universal entanglement, then the degrees of freedom in the waste part of the ancilla part of the system will be entangled by themselves. But what is true is that once you kind of get to the fixed point of this process, once you've done a lot of RG flow, then the kind of the refrigerated part and the ancilla part will be decoupled from each other. So you reach the fixed point of this process when there's no entanglement between the renormalized part and the waste part. So eventually they'll be separated from each other, but there can exist a lot of correlations within the waste part itself. And yeah, so you can kind of, this slide is saying that you can kind of formulate what we're trying to do from a more general level, where you think about some quantum channel, which is doing RG, and you can have some various properties that you would want such quantum channels to satisfy. I can talk about this more if people are interested, but I'm going to skip it for now. Let me just talk about how, like, the kind of sort of idea that we're going to borrow. Oh, we have another question. Sorry, let me read this Alex's question. Alex, I can't see your full question.
Alex, you can unmute yourself and ask if you wish.
So my question is, can you then perform the same RG flow using measurements and without using the ancilla degrees of freedom?
Yeah, good, okay, good question. So we are basically kind of measuring these ancilla degrees of freedom, and that they don't participate. I guess, yeah, I'll address that basically in the next slide. If I don't address that, then bug me again. But I think that I think I'll get that in the next slide. So let me talk about how I mean, I guess you can already see that on this slide there are a bunch of measurement symbols, right? So indeed. So let me tell you about the kind of like sort of kind of general framework that we'll be using to design these algorithms. It's inspired by some algorithms called quantum convolutional neural networks that Soonwon worked on with Iris and Misha a while ago. And the idea is that basically what you do is, we're interested in solving this problem of phase recognition. And so we should kind of structure the algorithm which performs phase recognition in a way that is kind of builds in some kind of RG-ness into it, right? So how we do that here is we stick our wave function in on the left, and then we act on it with some kind of like hierarchical unitary, a bunch of sequence of unitaries, which kind of like are arranged in some hierarchical tree to operate at different scales, right? And in this original paper here on the bottom, what these authors showed is that they showed that like by kind of like tuning parameters in this unitary circuit, which kind of looks like a Mera, if people are familiar with that. By tuning parameters in this unitary circuit, you get something which works, which does a good job at performing phase recognition. So we're going to try to basically design a circuit which looks like this, which we can prove does this phase recognition process. And here, okay, here hopefully I can answer Alex's question. So this is just kind of like another schematic picture of what this circuit is supposed to look like, right? So we have this giant box is our circuit. The bottom is the input, in which we put our kind of UV wave function. And then the circuit is built from this kind of hierarchical tree of unitary matrices. So it's this big like tree tensor network. Each of these blue shapes, I don't really know what to call this shape, like a hat or something. Each of these blue hats is unitary matrix, and they're chained together in this big way. And then it spits off things into the renormalized part and the ancilla part. And if you like, all of these legs, which are not kind of passed on to the next layer of the network, they don't participate in any of future interactions with any other degrees of freedom. And so you can just think of them as being measured, basically. That's where the little measurement symbols came from. Yeah.
So are these really ancillas in the standard sense, or this
No,
the number of input spins, let's say, is the same
Yeah.
as the number of output spins, or
Yeah,
you
it's
have
just-
to use
yeah,
extra?
I don't. I think the terminology ancilla is very suboptimal, but it wasn't clear what the better terminology was, so we just left it like that. It's basically just you get your input wave function on some n spins, and you choose some subset of them to act as kind of the bath, and some subset of them to act as the renormalized part. And you can view this protocol as you just kind of like, you eventually basically measure all the bath spins, and you leave some renormalized wave function on the renormalized spins, some subset of the spins. Yeah. So we're not bringing in any extra degrees of freedom. We're having the wave function act as a bath for itself. I mean, that's not to say this is the only protocol you could think of. You know, if you're in some system like Rydberg atoms or something where it's very easy to like bring in ancillas and entangle them with the system and then bring them out again, then you could try to come up with different protocols. But we're just gonna, use the system as the bath for itself. So I'm gonna go through this for a very simple example, which is the Ising model. This example may be a little bit too simple, and it's definitely overkill for this problem in the case of the Ising model. But I don't really want to like spend the whole talk talking about like symmetry fractionalization and SPTs and stuff. So I'm gonna, for that reason, I'm just gonna stick with this very simple example. I hope I don't bore people, but here's what we're gonna do. So we have the quantum Ising model in one dimension, and we want to distinguish. Say we want to build some algorithm which recognizes if you're in the symmetry breaking phase of this model. Right? So we're going to try to design this RG flow. Of course, like when you think about what a fixed point of this RG flow should be, the natural fixed point you would want for this this phase is just the product state of all spins, say up. Right? That's like a very good. There's no entanglement in that state. That seems like it could be a natural fixed point of an RG flow. So we want to design some circuit which does that. So we need to design a circuit that if you give me a wave function in the ferromagnetic phase, it'll output this fixed point product state. And if you give me something that's not in the phase, it has to not go to that point. It has to go to something else. Right? Okay. So how we do that is, as you were saying, with block spinning, basically, we just want to do this in a circuit, right? So again, I originally made the slides for a talk at Berkeley, so blue is winning all of the votes. So I apologize if you're offended by that, but I didn't redo the slides. Anyway, I guess this goes back to our conversation at lunch. But anyway, I'm just going to engineer blues to win all the votes here. anyway, so what we do is we do majority vote, and it's kind of very reasonable that if you start doing majority vote on your wave function, in a way I'll make clear in a second. If you start doing majority vote, then once you've sort of done a tournament of majority vote on a scale which is bigger than the correlation length in your wave function, then you'll have converged to the kind of ultimate fixed point of the system. Right? This is just usual RG that one would do in like a classical, completely classical spin model. But okay, but we need to do it in a unitary way because we're doing unitary circuits, right? So a majority vote is not an invertible thing because it could be unanimous or you could have it could be 2 to 1, right? But it's very easy to actually make this into a unitary transformation. What you do is you kind of it's illustrated here on the left. I've just written this as like the notation as if it's a general group, right? But here we just have up and down, it's just Z2, zeros and ones. And what you do is you basically, it turns out that the mapping from 3 spins to the majority vote plus the values of the domain walls that you see in these 3 spins is an invertible transformation. So what you do is you just say like, is there a domain wall between these 2 spins? Is there a domain wall between those 2 spins? Keep track of that information and then always also keep track of the winner of the majority vote. And that's just some invertible transformation on 3 bits to 2 bits. And so you can design a unitary circuit which does that.
So this is just the quantum error correction coding for the repetition code.
Yes, so this is why I said I had this slide that says like you can think of error correction in the back of your mind if you like, right?
Can you repeat what you said?
This is the quantum error correction interpretation, the quantum error correction protocol for the repetition code.
All right.
So
It's not really quantum error. I mean, we're using some quantum gate to do this, but this is just like completely classical. We just trying to preserve we're trying to preserve like one logical bit of information, which is like the magnetization of the system, sort of. Kind of a technical point is that we don't actually care about getting the logical information correct, in the sense that I don't care if I'm not going to be bothered if like gerrymandering occurs in this example, right? So if I have an input where there are more upspins than downspins, so there's a net positive magnetization, that's in the symmetry breaking phase, and I'm not going to care if my algorithm accidentally like sends that to a fixed point where all the spins are down. As long as it correctly gets the fact that there's symmetry breaking, then I'm going to be fine with that. So you may sort of lose the logical information about the actual winner of the vote if there's gerrymandering, but we just want to know, are you in the phase where the symmetry breaks? And so for us, we're good. Yeah, so we just do this majority voting in a oh, here's your comment. Yeah, there's the error correction thing. And then you just do this majority voting in some big tree, right? And I guess on this slide I've put these little measurement symbols to indicate that those kind of degrees of freedom just don't participate in the further process. Okay. So that is basically it for the Ising model. So I think that's pretty kind of trivial, right? But it's kind of overkill for the Ising model because for the Ising model you just have like there's a local magnetization that you can just measure, right? So why do you do this super complicated like tree tensor network on your wave function with all these huge quantum gates? Like you just just do one-shot measurement of the magnetization and be done, right? I'm not going to argue against that in this case, right? However, in general, it's not going to be clear what the right order parameter is. Like you may not know, say, the basis in which to measure the magnetization, or there may not even be like a local order parameter. Right? So for some more sophisticated examples, which are actually the examples that motivated us to do this project, namely examples where you have topological order, you won't have some local order parameter that you can go in and just like measure, right? So you need to figure out a way of doing this RG flow, which is not just like trying to amplify the value of some local order parameter. And then the final point is that, yeah, maybe you don't know what the errors are, right? Here the errors were just spin flips, but in this more general setting, it can be more complicated. Yeah.
Just wanted to clarify before you moved on. What you don't have is one quantum circuit for every phase, such that you can take any state within any phase and it can put it in its right category. You have one quantum circuit per phase.
Yeah.
And then if you have something outside of the phase that it's assigned to or designed for, it sends it. Where does it go? Like, is it spit out nonsense? Is that how you know that it's?
Yeah, it basically spits out nonsense. Yeah. So
Okay.
for the examples that we're going to be we're going to be thinking about, what happens is that sort of imagine doing the following. Imagine you act with the circuit, and then you trace out the garbage degrees of freedom. Well, the non-renormalized bits, right? You just trace out over the values of those guys. Then what we want is basically that you flow to the maximum UX state if you're not in the phase. So you just kind of, if you just look at the renormalized spins and you're not in the phase, then you do a bunch of flow and then it just looks like noise, basically. Okay. So but yeah, indeed, it would be totally useless if like everything went to the fixed point, right? Then this would be completely useless. So establishing that indeed happens is very important. Yeah. Yeah, cool. So so because of these points, you know, it's so the existence of phases in which these points occur kind of motivated us to actually think about this problem from maybe a framework which is hopefully more easily generalized to these kinds of settings. So kind of an intermediate sort of class of examples which are like kind of complicated but are actually really pretty simple in some other ways is the case of 1D symmetry protected topological phases. They don't have a local order parameter, but they're still very simple. And so we kind of think about detecting them using this kind of circuit. And so that's what I'm going to talk about for the rest of the talk. Yeah. So I'm going to try to, we'll see how this goes. I'm going to try to, yeah, I don't know what the kind of background people have here. So let's just see how this goes. If it starts being incomprehensible, like let me know. So here is here's what an SPD phase is. It's basically it's a one-dimensional for us phase of matter, which has some symmetry group that is unbroken in the ground state, but is nevertheless not trivial, right? So for example, in the Ising model, the paramagnetic phase preserves the symmetry, but it's also pretty trivial because the paramagnetic phase is just the ground state that you would think of there is just a product state. Okay? But it turns out that you can have kind of symmetric phases which are not trivial in a very subtle way. And the usual way in which we think about talking about this is in terms of this property called symmetry fractionalization. So I'm going to try to explain what that means. So imagine we have some, we have this symmetry, right? And imagine that this symmetry in question here is just some nice local symmetry, like the Z2 symmetry of the Ising model where it just acts on each site. Right? And consider acting with that symmetry on some finite region of sample. It's like you're applying a symmetry transformation only on some subset of space, right? Now, if I acted on the entire wave function with this symmetry operator, then it would be the wave function would be invariant because I'm thinking about symmetric phases, right? But if I just act on a finite interval, then you can kind of like sort of create excitations basically at the ends of the interval that I act on, right? And it turns out that kind of like different distinct choices that you can make for the way in which this this interval symmetry operator fails to act as the identity are kind of distinguish what kind of phases you have. Yeah, basically what we say is that here the action of this operator R, the symmetry generator on some finite region, is equivalent to acting with these two guys at the ends. And these two guys at the ends transform under some group representation, and the kind of group representation they transform under determines what phase you're in. So like if people are familiar with the Haldane chain, this is like the classic example where you have some phase with an SO3, for example, symmetry group. And when you do this, you're left with operators at the ends which transform under some representation of SU2 instead of SO3. Anyway, so there's some algebraic data which classifies how they're different. Okay, so that made this kind of a very abstract point of view of what the SPTs are, but we're going to go with that definition. And what we're going to try to do is we're going to try to design a RG flow circuit to recognize these kinds of states, right? And that means that first we have to figure out what the notion of a fixed point should be for these phases, right? So for the Ising model, the fixed point that we're looking for is just all spins up. So what should the fixed point look for? We should look for here. Yeah, basically what happens is that we can always choose a fixed point which is exactly stabilized by these operators. So there's some collection of these string operators which measure how the symmetry fractionalizes in this space. And our fixed point is just going to be defined as the wave function such that when you act with this operator on the wave function, you get the just one for all possible operators. So yes, and so then what we have to do is we have to figure out how a given wave function in this phase we're trying to detect can be written in terms of like errors which have been applied to this reference state. And then we need to figure out how to correct them, right? So for the Ising model, it was obvious we had our reference state was all spins up, and then there were some like spin flips, which were these errors which were applied to the wave function, and we had to like correct them. And so we need to figure out what the analog of that is in the case of these SPT wave functions. Okay, so here's how we do that. We do that using the following perspective on, like, maybe it's not a perspective, more of a definition of what SPT phases are, which are that they are basically equivalence classes of local symmetric unitary circuits. So what this means is that if I have any two wave functions in this SPT phase, they're related to each other by a short depth local unitary circuit where all of the gates in the unitary circuit are symmetric. So you can kind of think of like this yellow phase over here is everywhere I can get from, say, this given fixed point by acting with some like a short amount of symmetric unitary stuff, right? So a short amount of symmetric unitary stuff is not going to like make the wave function super entangled, right? So all of these kind of wave functions are kind of weakly entangled, and they're all symmetric. And it's kind of like each one of them is just the kind of the space of wave functions that you can reach by doing this not very highly entangling symmetric time evolution, if you like.
Is it true that every SPT
That's this.
is bijective? Like I can understand that the class of states you can reach by short unitaries are in the same SPT phase.
Yeah.
But is it true that every state in the same SPT phase as a given state can be reached by a short unitary?
Yeah. You can kind of show that using some matrix product unqualified yes in one dimension and yes in higher dimensions, maybe by definition actually. So kind of what we have to do is, phrased in this language, what we have to do is we have to design this machine which kind of like undoes any constant depth symmetric unitary circuit, right? So we have like what this is illustrating here is that we picked two different wave functions in the same phase. They're equal to different these kinds of circuits acting on this reference state, and we need to be able to like undo each of these to kind of like look at the order that's present at the bottom of the circuit. That makes sense. So we're trying to like undo these kinds of circuits. So how can we do that? Well, it's uses the following fact here, which is that I can always decompose the action of this constant depth symmetric short range unitary thing in terms of a bunch of local symmetry actions acting on the wave function. So what that means is, again, think about the Ising model, right? The claim is that in the Ising model, you can think of the same kind of like circuit-based picture for phases in the Ising model, right? So any state in the ferromagnetic phase of the Ising model, I can get from the all up spin state by acting with some short depth symmetric thing, right? And the claim is that that short depth symmetric thing can always be the action of that short depth symmetric thing can always be decomposed in terms of a linear combination of local symmetry actions, which in the Ising case are just spin flips, right? So all I'm saying is that any wave function this is kind of a trivial statement. Any wave function in the spontaneous symmetry breaking phase of the Ising model, I can get from the reference state of all ups by just applying some spin flips, right? And importantly, the kind of correlations between the different spin flips are local if I have done a short amount of unitary stuff to it, right? So I'm faced with the problem of kind of like decoding these errors, where the errors are like, some statistical configuration of spin flips that have some kind of like spatial correlations, and I need to like decode those kinds of errors, right? That's kind of what we want to do.
Can any state be written as a linear combination of symmetry operators applied on the reference state?
Yes,
Like,
yes, yeah, good. So I need to emphasize this point. So any state, regardless of whether it's in the phase or not, any state which is symmetric can be written in this form. But so that's kind of a triviality. But the important part is that if you're in the same phase, if this wave function little psi is in the same phase as this fixed point state, then the kind of correlations between these errors are kind of limited in their spatial extent, right? Like if I want to basically saying that the correlation functions of Z operators, connected correlation functions of Z operators in the spontaneous breaking phase of the Ising model are short ranged, right? Because we've only applied like a kind of constant amount of noise to them. Right? So if you let these like the correlations in the errors be very, very large and extend over the whole system, then you will be in a different phase. The point of this is to say that like you can kind of reduce the problem of doing this phase recognition thing to the problem of identifying and correcting these kinds of errors, right?
Mm-hmm.
So there, even though we're kind of phrasing this in a very general way of like we just have some wave function and it's obtained from the fixed point by some unitary circuit, that sounds very general, but you can just rewrite that in terms of I've had like a bunch of errors that I've applied to my wave function. I just need to go and like correct and detect for those kind of errors.
So you're just defining your SPT phase as your code subspace.
Yeah, basically, yeah. The fixed point is, yeah, that's right. Although again, we're not concerned about preserving the logical information per se, because
so your goal is to just find
our goal is to like, yeah, it's a little bit. So our goal is to kind of like correct for the errors, but we don't care if we make a logical, if we accidentally perform a sort of logical operator. Maybe I shouldn't say that. I'm saying this because SPTs, you can code like information in their degenerate ground states on like an interval, right? They have.
Yeah, I don't care about that.
Okay, then you don't care about then ignore that then. Then we're just trying to decode. So we're trying to decode, and we're able to do this decoding just by representing the unitary circuit in a way that makes it look like a bunch of errors. Right. Okay. So that's the point. How do you make a generic kind of unitary circuit look like a bunch of errors that you can then correct? And that's done using this kind of relation. And then once you get to that point, once we get to this point where we said that I've kind of like turned a unitary circuit into a bunch of errors, then all you have to do is you just have to come up with some algorithm which like finds the errors and corrects them, right? Then at that point, then you just have to come up with this algorithm. Then things kind of become a little bit specific to the particular type of phase that you're looking to classify, right? So you kind of break it into two parts. First, turn your unitary circuits into errors and understand how those operate on your wave function. And then part two, get rid of those errors, right? So for these SPT phases, the first part, understanding how the unitary circuit acts as a bunch of errors, is actually very simple. And then the correcting of the errors is like
Just correcting the generators.
Yeah, so you just have to figure out how to kind of like do majority vote, essentially, on these kind of more general errors.
Is that the most efficient way to do it?
I don't know. Maybe not. I'm gonna choose to.
I mean, if it works, it works. But
It's kind of like when you're doing block spinning, right? Like, why do we do block spinning? It's a very simple thing, and you could come up with other protocols that you like, but they're probably sort of universal. As long as you have some flow on your probability distribution that converges in some way. Then it'll work.
I'd be interested to see what would happen if you tried to use some of these more topologically motivated forms of error correction,
Like,
toric code.
oh, like how we would do the correct error correction for that? Yeah, that's what we could talk about that at some point. So that's what we'd like to do, right? There, in that case, let me just address that point now. So here, why these kind of SBT phases were very simple is that the errors were all these symmetry actions. So kind of you only have, if you like, you only have errors which are bit flip errors. You don't have any phase flip errors because we just have the symmetry action, right? If I'm thinking about a more general case, like I want to perform such a flow on a phase with topological order, then I can't restrict the kinds of errors that happen on my system in the same way. So I have to consider, say, both phase flip errors and bit flip errors, and you need to understand how you address both types of errors at the same time. So I have some ideas about that, but that's like that would derail us if I start going into this. So I'm going to skip most of this section because it's only going to be interesting if you're like a hardcore SPT person, right? But the point is we just need to do this error correction identification process. And yeah, I'm going to just tell you that it can be done using tensor network methods. It's very simple. So sort of like the way you actually construct this device is you use the group theory data, which distinguishes one of these phases from the other. And you take that group theory data and you make some tensors out of that group theory data. And then you take those tensors and you stick them together in some way. And you get this unitary that appeared in our circuit. And then you can prove that this, if you use the unitary circuit with this particular thing, where this is constructed from this group theory data, then the RG flow works and all that stuff. Okay, but yeah, I mean, I don't think.
Can I pause you for a minute?
Yeah, sure.
I'm very confused. Like the symmetry actions were to distinguish all these states that are around a given fixed point, around in a phase, right?
Yeah.
And they're not distinguishing different phases.
They are distinct. The job is basically if you input a wave function in the target phase, doesn't matter where it is. It doesn't have to be close to the fixed point. It can be anywhere, right? Then it'll flow to the fixed point. And if you give me something that's not there, then it will go to something else.
Okay.
So does that?
Yeah. Okay. Yeah. Sure.
Let me see. Do I want to talk about this? Yeah, sure. I'll talk about this. Why not? So one thing that's kind of interesting here. So okay. So this is just a summary of what I was saying, right? So we take our wave function, we stick it, and we get this fixed point plus some garbage. And then at the end, now we have to we've gotten our fixed point, and now we have to decide what phase it's in, right? So eventually we've simplified the problem because we have this very nice, pristine, Platonic ideal of a fixed point state right here. And we just need to now say, okay, what phase is it in? So we need to perform some measurement on that renormalized state so we can distinguish what phase it's in. Right? And what we do is we measure these string operators that I had put on a slide, order 10 slides back, where we had this symmetry action on some interval and then some things that decorated it. And we measure those operators in the renormalized state, right? And then basically if the expectation value of that string operator in the renormalized state is 1, then that wave function is in the phase. And if it's 0, then the wave function was not in the phase. Okay, so I'm just trying to say that we're just measuring the expectation value of some simple operator in the renormalized space. But what you can also do is you can equivalently think about this as, since we're just doing a big unitary circuit, I can either measure a simple operator in the renormalized space, or I can measure a very complicated operator on my UV wave function before I do any flow, right? So I just, how that works is I take my simple operator that I'm measuring at the end, and I conjugate it by this giant unitary circuit, and I get some mess. I just measure that mess directly in my input state. And they'll have the same effects, right? So I'll be able to also do phase recognition with this process, which is saying that there exists some universal, very complicated but universal operator that I can measure, and its expectation value will be 1 in the SPT phase and 0 outside of the SPT phase. So this kind of gives us an explicit construction to construct that operator. It's kind of like a renormalized string operator, if you will. And the point is there's one sort of daddy universal string operator which just does the job for the entire phase. Yeah, cool. And then, yeah, of course, to check some boxes, we can do numerics and run this kind of like protocol on some wave functions you generate. You know, when you're doing numerics, it's fun because you can like do things like you get your wave function in the phase and then you do a bunch of crap to it. You just do some like random unitary things to it, some short depth unitary circuit, and you can try to check that our algorithm correctly kind of like undoes the action of those random circuits. Anyway, so good exercise to build character, but I won't.
What is the depth of the circuit? Or?
Oh yeah, exactly. So what? If I'm showing this plot, I have to explain it, right? So what we're measuring is the expectation value of this operator at the end of the circuit, and what this plot means is that this parameter here on the bottom lambda is kind of like tuning us across a phase transition, and we're getting the ground state wave function as a function of lambda from DMRG, and then we're exactly as you said, we're applying a variously deep amounts of RG flow, and then seeing how well we can that order parameter detects the phase transition, and you can see it's kind of like getting more confident, closer to the fixed point as you do more layers of this RGF, as to be expected. I mean, we can prove that that's the case, so it would better work out. But yeah, yeah, and then to end up to end, you know, we already just
Can I
discussed.
ask you a quick question? So
yeah.
At the end of the circuit, how close are you really to a product state, or you're still in a highly entangled state?
Yeah, you mean
It's your reference state.
the reference state? Yeah, so the reference, the kind of what you can show is that well, at least the way I like to phrase this, if you're asking about the entanglement of how highly entangled is the state you get off, you get, right? So what you mean is like, if you look at the renormalized degrees of freedom, how highly entangled are they, right?
Mm-hmm.
Okay, but you're kind of asking about like the entanglement within some subsystem, which is just the renormalized spins, right? So in order to ask that question, let's trace out the ancilla spins, if you like, and just get those away, right? Okay, when you trace out those, you'll actually produce a mixed state in general, right? Because the renormalized spins can have some correlations with the garbage that you threw in. So you'll produce a mixed state. But what you can prove is that any entanglement measure of that mixed state is monotonically decreasing under this flow. So if you look at things, because it's a mixed state, you can't just compute the entanglement entropy, right? Because you'll kind of get some mixed in there.
Right.
Anyway, if you compute an entanglement measure like the nextity or something, it's monotonically decreasing. And if you look at but looking at something else like the entanglement entropy itself is a little bit hard because that may be non-monotonic under this protocol. But eventually what happens is that you get to, we've designed our fixed point to be the wave function with the smallest amount of entanglement conditioned on the fact that it's an SPT phase. So you're reducing entanglement as much as possible. And when you get to the fixed point, you kind of just are in a steady state situation where you have a small amount of entanglement on the renormalized degrees of freedom, and they are unentangled with the reference, with the ancillas. But it may take a while to get to that point. In fact, but we didn't really, I think it would be a good thing to do, but we didn't really like, you could try to imagine like proving some theorem that says like such and such information theoretical quantity, the flow of it under this map is this, right? Or like such and such quantity, you know, the decrease in this quantity under the RG flow is bounded by something, right? We didn't really take that approach, but I think that could be useful to do in the future.
No, Name question, but if you go back one more slide, so you're saying that you're measuring this operator, right? The string operator at the end of the the circuit. But you threw away a lot of garbage into the this additional degrees of freedom. So how do you define your string operator after you've done this?
Oh yeah, you just do the string operator only on the renormalized part of the. It's like if we were doing the Ising model, right? You're doing this flow and you're getting your renormalized state, and then you're getting your garbage stuff. Like the garbage is storing the values of all these domain laws that you detected when you're doing error correction, right? And you don't want to. I mean, you can look at correlation functions of operators supported on that subsystem, but they're going to be very complicated. And it's going to be all this garbage stuff, right? Correlations between the garbage, blah blah. But instead, you just look at correlations that's restricted to the renormalized subspace. So that's what we're doing here. We're just looking at the string. This is kind of like what I've tried to illustrate with this picture. We measure a string operator on our like renormalized part, and we just don't do anything on that part. Cool. So then I'm done. Basically, we were already talking about this topological ordering. That's up there. You know, I was kind of interested in like what we've kind of done is we've basically just taken like, you know, this block spinning idea for RG and like we've turned it into a unitary circuit and made it more sophisticated for these topologically ordered things, right? But maybe that's not like the best quote way of answering this phase recognition problem, right? That's like that's something inspired by like kind of very well established physics things in RG, but maybe that's not the actual best algorithm, right? Like maybe in some system where ancilla qubits are very cheap, we can like pump a bunch of ancilla qubits in and like entangle them locally with the system, then pump them out, and then bring fresh ancillas in and like literally act as a kind of more like a refrigeration cycle like that with fresh qubits. Like, can you design some RG system that looks like that? What are better ideas along those lines? I don't know. Yeah, but anyway, that's basically all. So thanks for sticking through it, and stop there.
Okay, thanks for the nice talk. Are there any questions or questions from the Zoom?
Yeah, I have a small question. So at the level of Hamiltonian, it would be equivalent to ask which eigenvalues remain same.
Which eigenvalues remain for which part?
For the for the fixed state.
Yeah.
And when you apply your other operators, that takes you here and there, and you separate them out. So it's kind of like preserving some global untouched part, and the symmetry operator are acting on some parts which we just discard out. So there is some untouched part in the wave function in the state.
Yeah.
So at
that untouched part is kind of like hidden. It can be hidden in some kind of tricky way.
Okay. So if I want to think it like in terms of Hamiltonian, would it be like equivalent to asking which eigenvalues remain fixed in that phase?
I don't know, because we can have what the ground state or any state of the Hamiltonian looks like will change. I mean, so I guess you're saying, so we could track an effective Hamiltonian by conjugating the Hamiltonian of the fixed point state with this giant circuit or something, right? And then look at what that does, right? I think that kind of just produces a big mess. And I don't know if there's anything simple to say about like the flow of the spectrum of that Hamiltonian anyway. I think we're focusing on the wave functions directly is a bit simpler within this kind of approach to things. Yeah, kind of when you're designing a unitary circuit, it's better for some reasons that I can talk to you about later. So thinking about the flow at the level of Hamiltonians, I'm not sure is exactly the right thing to do.
Yeah, also because you have a group structure here in equivalence classes, are they are these flows like cycles or beats?
Oh yeah, well hopefully not. We want that would not be very good for us from the point of view of distinguishing one phase from another, right?
Yeah.
So we definitely avoid those kinds of limit cycles.
The mark.
Question also from how does your algorithm do random measurements?
Oh, sorry, wait. I don't know if I can.
Yeah, you can click on the chat.
Here we go. How does algorithm do versus randomized measurements? Randomized measurements. Are you talking about like doing tomography, or are you thinking about like measuring, say, the string operator in random bases or something?
Yeah, maybe I can say it out loud. I guess I'm talking about this randomized measurement toolbox that like a bunch of people wrote a paper about last year.
Yeah.
Preskill, Flamia, all these people.
Yeah,
I'm not sure if that applies here, but yeah, that was here.
That's kind of useful if you want to like do tomography or something, right? So you make like a bajillion measure. Well, not a their whole point is that you don't have to do a bajillion, but you make some measurements that allow you to kind of like get a compressed version of the wave function, right? That you can save on your computer. So I don't know, like in this kind of situation that we're imagining, we're kind of given the wave function, and our goal is not necessarily to like do tomography and reconstruct what the wave function is. We just want to know about this like the kind of order present in the wave function. So I don't know if randomized protocols necessarily. I don't know what a good like randomized measurement protocol would be in this particular case to try to accomplish that objective. But that could just be a function of the fact that I am not too familiar with uses of this kind of like randomized measurement protocol. But sort of like this, the goal, like I was saying, like the goal that we're trying to accomplish is pretty simple, just some recognizing whether we have one phase versus another phase. And it doesn't really require, it's kind of closer to the end of just measuring an order parameter than it is to doing tomography, right? So since our goal is kind of simple, I think that doing an approach which is sort of closer to can I find sort of the right order parameter measure is going to be easier. Yeah, I don't know if that helps.
Yeah, thanks.
Okay, so no more questions. Let's thank the speaker.
Yeah, so what if the ground state lives very near to the phase boundary?
Yeah.
What will happen to?
Yeah, so if the ground state is very close to the phase boundary, well, so we have to talk about like, I think the sharp statement is that it depends on the correlation length of the wave function, right? So if your correlation length is very large compared to the system size, or by which I mean it's like a constant fraction of the system size, then our algorithm is not going to be reliable, because sort of you have to run the algorithm for a number of layers, which is like the log of the correlation length. And you want to be left with a renormalized system, which is not just like one qubit, right? Because you need to do some measurements there. But as long as the ratio of the correlation length to the system size is small, which is kind of the only that's the only setting in which you would say you're actually in that phase, is if the correlation length is small, then you'll be fine. So in general, you expect that the convergence of the, actually, how do I go backwards here? Here we go. In general, what you expect is that the sort of convergence of your algorithm is exponential in the number of layers you apply, and that's what we see numerically in this plot. So that kind of tells you how long of a correlation length you can tolerate. Just you need to go for a depth, which is the log of that.
So it will completely break down right at the phase boundary.
Yeah, but that it has to, right? Because right at the phase boundary, you don't know what phase you're in, so our algorithm can't really. If it converged to the fixed point, then it would be telling us something wrong. Right? So.
Thank you again.
Yeah, no problem. All right, bye everyone on Zoom.